Alright, we're moving on to the next section, which is on exponential functions. Now, exponential functions are study the class of functions that have this form. Sum b times a to the x. So what you have when x is 0 is just the value b, so that's your initial point here. In our case here, b is 1. And then as x increases, it increases by multiplying together powers of a. And so in our case, a is 2. So what's happening here is we start at 1 and we double every step we go forward. So we go from x is 0, or sorry, when x is 0, the value of the function is 1, 2, 4, 8, 16, etc. Now, this is a very interesting function because even though looking at it, it seems to bear no resemblance to a line, it is very similar in spirit to a line. What is a line anyway? It's a function determined entirely by two parameters: the slope, which determines how fast the function grows, and b, the initial value or the y-intercept. So in this case, b is 1, m is 1, and we have this particular line. If I change b, I change the initial value. If I change m, I change the rate the function grows. Right? And what's happening here is I'm taking a b and I'm adding to it x copies of m, right? So this is all addition in a sense. All multiplication is reiterated addition. Now, what's happening in an exponential function is I'm taking b and I'm multiplying it by x copies of a. So in a sense, exponential functions are really just the multiplicative analogs of linear functions. I have b, which determines my starting point. So if I start, my b equals 2, then boom, when x is 0, this thing takes on the value 2. And then I have an a, which determines how fast it grows. So in this case, a is 2, so it doubles with every step forward. If I lower it some, it grows at a slower rate. If I let it be 1, then I'm just multiplying by a bunch of copies of 1, which doesn't do anything. And then if I decrease it, then it's I'm now, in this case, I'm multiplying by 10% every time it goes forward. So it's decreasing as I go forward and increasing as I go back. And so in a very, very real way, we have a function that is in all ways like a linear function, except with multiplication playing the role of addition and exponentiation playing the role of multiplication. So what's going to follow next is that I'm going to show that exponential functions have basically the same properties as linear functions with respect to the fact that you can totally determine an exponential function by a point and a rate of growth, or by 2 points. But before I conclude this video, I'd be remiss to point out, if I didn't mention, that we in a sense have already seen exponential functions. It may not have occurred in exactly this form, but we know from earlier that we were dealing with functions of the form something like future value is equal to present value, maybe 100 times 1 plus 0.01 to the x, and something like this determined the value of a debt or an investment over time, where this is your interest and this is how much initial debt was, and that stands for time. So when we dealt with financial mathematics, all of those things were modeled by exponential functions. And really, exponential functions model any sort of thing where the growth or decay is somehow proportional to how much stuff you have. So, for example, the more debt you have, the more debt you accrue. So that's an exponential function. If you have a population of people, the more people live in a country, the more people are born into that country. And so things like population uh, of human beings or of organisms of various sorts are modeled by an exponential process as well.